I wanted to talk about Newton's third law, which is weird in that almost any adult can quote it at you. For every action, there's an equal and opposite reaction. But I would say almost none of those people understand it. A much better way to say Newton's third law is that forces come in pairs, and that the pair of forces is identical, it's on two different objects, and it's opposite in direction. And furthermore, the agent and victim get switched. So what do I mean by that? Let me give you an example. So I got this table here. I'm going to punch it. We could say Dowd punched the table. But because of Newton's third law, we also have to say something else. The table punched Dowd. And that's a weird sentence to say. And it sounds kind of awkward, but it's the reason that my hand kind of hurts.
Let's take a look at the forces involved in me punching the table. I have a similar situation up here for someone named Colin who apparently has punched a wall. He's put a force on the wall. I've labeled that FP Colin. You can see it's on the wall. But his hand is probably going to hurt afterwards because there's an identical force. I drew it the same length. It's on him now, and it's in the opposite direction. So if we were going to describe these two forces, one of them is Colin punched the wall, and then we just reverse agent and victim. The other force must be the wall punched Colin. You can do this for any force there is. There's always a paired force.
There's no force that you can describe that you can't switch the thing causing it and the thing being affected. And if you start thinking about it, it starts getting weird. For example, you know that things fall down because of gravity. In fact, you know there's a force of gravity on me right now. So you could say the Earth is pulling Mr. Dowd. Do the Newton's third law pair. Does that mean Mr. Dowd is pulling the Earth? Yeah, it does. Did you see the Earth fall up towards me? It did. Just a little bit, though. If you look on the board behind me, you'll see the math that describes why the Earth didn't move that much, but I moved a lot.
So I'm making the claim here that I pulled the Earth just as much as the Earth pulled me. And up here I say that those two forces are equal. The force of gravity caused by the Earth equals the force of gravity caused by me. But we have to remember F equals ma. So me, with such a small mass, to make up for that, I get a large acceleration. My mass is only 115 kilograms. Look how big the Earth's mass is. With such a huge m, it ends up with less a. So that's the reason we sometimes have a hard time seeing Newton's third law. Just because those forces are equal doesn't mean they have equal effect. The mass is going to play a big role too. Let's look at another situation where it's hard to believe that two forces in a pair are the same.
So I've got here a bowling ball and a ping pong ball. I'm going to have them crash into each other. And I want you to predict which is going to experience more force. Here we go. Watch that again in slow motion. So this is the same trick question it always is. If you were thinking the ping pong ball had more force because its motion changed more dramatically, you're forgetting that the ping pong ball also had much less inertia. It changed its motion more because it was easier to move. If we had a force this way from the bowling ball on the ping pong ball, we had to have the exact same force in the other direction on the other objects. The two forces were equal and opposite. Why is there such a much larger acceleration of the ping pong ball? Well, if these forces are equal,
we got to remember that they both equal ma. Since the bowling ball has a very large mass, its acceleration is pretty small. Since the ping pong ball has a very tiny mass, it ends up having a big acceleration. Let's look at another common situation where Newton's third law confuses students. I want you to think back to Spirit Week when the classes have a tug of war against each other. And I want you to think about a tug of war that was won by the juniors against the sophomores. Newton's third law makes that a little hard to understand because according to Newton's third law, these two groups pulled on each other equally. So how is that possible if one group won? The reason is that we can't just consider one force on each group of students. We have to consider all of the forces on both of them. So when we do that, we see that the reason the group that won accelerates to the right is that they were able to push off the ground with a bigger force than the other group. If you look at the sophomores who lost, they have a bigger force to the right. The juniors who won also have a bigger force to the right. So both groups are going to accelerate right. The forces between them may be the same, but it's the difference in the other forces that cause the difference in motion. So this does not contradict Newton's third law.
And Newton's third law is something to keep in mind is true for all forces. Every force has a pair. I wanted to finish with one other demonstration with these spring scales. They look kind of fancy, but inside here there's just the spring like the other spring scales you've seen. And to be honest, they're not that good. I've got one here on the pole, and I'm going to hold the other one. And I'm going to pull on the pole. So this spring scale will register how much the pole is pulling on me. This one will register how much I'm pulling on the pole. Of course, according to Newton's third law, they have to be the same. And we see that they are. Now, it's not perfect because they're kind of cruddy spring scales, but they do move together, and they always have approximately the same reading.